So from here we can deduce the Voronoi complex. Sorry, what I went to be, because we were discussing something, I wanted to speak about it on the blackboard, sorry. But before that, I mean, you see that for n equals 7, we already have a large number of cells. So the complex is very, well, reasonably large. You have 20 billions of cells, only for rank 7. And if now you look more closely to the homology, I mean, you have almost nothing. Okay. So again, you are spending most of your time computing 0. That's a clever way to use power energy, for instance. And again, we are sad because in first, when we have few rank 1 modules, and of course, no high torsion.
No torsion at all.
Yeah, but here we are killing all the generic torsion. Yeah, always. No, we have torsion. But the problem, honestly, I have absolutely no idea. I mean, of course, I mean, we could have fun and just compute this complex integrally. But the problem, I do not know what is the mathematical meaning then of the complex when you compute it integrally.
I mean, it would be GLN7 with Steinberg focus, right? No?
I'm not 100% sure of that. We have to discuss. So, yeah, well, sorry, hold up. Sorry. Yeah. Okay, I will discuss something in a few minutes. So, yesterday I spoke about the Euler characteristic of the group. People from the lattice community call a formula mass formula, so it's the same. After all, we are speaking of cohomology of groups, so it is nicer to speak of the Euler characteristic of the group. So we have seen yesterday that as soon that n is greater than 2, the Euler characteristic of SLN is 0 by harder work on the so-called Gauss-Bonnet formula. And as you see, you end up with, as I told you, a nice way to write down 0. Because it checked out that very likely we have computed the complex. We are not missing information. So if you randomly remove some cells or if you do some mistakes, I mean, it is no longer 0. You can believe me. So I'm not saying it is 100% bulletproof, but it is really a pretty good checker. And if you add the differential, it is also crazy. I mean, there are also other stuff that we can use in order to check. But again, it is not fully certified computation. Wow. Right. As you know, mathematicians also can do errors, maybe not necessarily fully certified computation as well. So for SL7, so you have a larger one, funnier, and again 0. And so it's very nice, of course. The day that we get this formula, we were particularly happy. And one thing more or less intriguing, because there are good reasons for this, is that at top level, there is a non-trivial class that we have for all n, and this class also appears in the lower case of Hermitian case computed by Dutour, Gongol, Gunel, Semke, Schaumann, and Yazaki in 2016. So we have the same class, and already at the time we believe that this class always exists, but we are not able to prove it. Let's say abstractly speaking, but yes. Oh. Sorry. Three
finger swipe, yeah.
Okay. So this is an open problem. I'm afraid also maybe a little bit hard. More interesting, and I'm afraid. So as you will see in a few minutes, we also get an explicit non-trivial class at this level. And gives you, in theory, a non-trivial class for K5Z. So it gives you, because we are able to compute that it is this, well, it is coming from this class. You could expect this non-trivial class to be the Bohr regulator, when the Bohr class related to K5Z, maybe up to a rational factor, so maybe up to a 2 or likely a 2, something like that. But we cannot, and likely very difficult to prove, but there could be at least a first heuristic by trying to compute the value in some suitable cohomology. Suitable, let's say, cohomology like the Deligne-Bellinson cohomology will be just a numerical approximation, of course. It will.
What do you mean by you can't prove that this is in the state?
Yes.
Yeah. It has to be that class.
Yes, but it has to be. But
what do you mean you can't prove it though?
I cannot prove that it is exactly the Borel class corresponding to the regular. So there could be a factor, for instance.
Oh, okay.
Yeah, but maybe we could prove a little bit more than saying here. I agree. So what I mean, you see, I mean, when you have 0, it's very easy to relate things together. But when you have a non-zero class, things are a little bit harder. Okay, so before jumping to this, so you can help yourself if you want to recall what already Jennifer and Peter has explained. So I want to be back on one point, which apparently was not clear. Sorry. So it is computationally related, but it's somehow more or less in one of the crucial points. So as I said, so suppose you have H rank n perfect form, and let's say you have V1, VMH, H, sorry, it's a set of minimal vectors. Okay, and so I can again order it. And now I can look at the gamma action on it and the number of representative gamma. And so you will get another set, let's say V1 bar, V1 bar, let's say M gamma bar, and this, of course, I mean, well, yeah, so this will be the core, I mean, it will be the core ingredients of the codimension 1 phase. Mod gamma. And here, what you will have will be just, what I mean by that is that for some phase, for some codimension 1 phase, you will have just few representatives. I mean, sorry, let's use the notation that I just explained. For some codimension 1 phase, just 1, 2, 3, or a few number of representatives. Okay. So this is, let's say, the scenario 1. And in this case, the geometry is easy, of course. Okay, so it's easy geometry and fast computation. Because the combinatorics is simple. So this is the test case scenario. And now you have the second scenario where the number, let's say number of representative of the codimension 1 phase is maximal mod gamma. This is that the number of minimal your cell is exactly the number of mod gamma representatives. So this is the worst case scenario. And this is the worst case scenario.
What does it mean to be maximal mod gamma?
maximal, it means that each minimal vector defining the codimension 1 face is a representative.
Okay.
Okay. And so even if the cell is simplicial, this case could happen. And in this scenario, even if the cell is simplicial, it is not going to help you that much, because the is going to be a nightmare, nevertheless. So, okay, so for n equals 7, let's say it is no problem. We can deal with this level of combinatorics, but already for n equals 8, it starts to be a bit more difficult. So the difference between this and this is that if you perform let's say, the Voronoi complex part associated to your perfect form, in this scenario, you can do this in few seconds. I could do this with my laptop and show you that it is doable in 1 second, even in rank 9. But in this scenario, for rank 7, even for a simplicial case, I mean, it will require few minutes. And for rank 8, a full day. Okay. You can think that this will happen. So unfortunately, we have some cells which are of this type. And so, of course, when you will be further away from the simplicial cells, the combinatorics of the geometry is going to catch you. And it will slow down the computation, but nevertheless, it is not slowing down the computation the same way you were performing a barycentric subdivision on it. But because this is also an answer to the question. So if you subdivision on such a large, already large simplicial face, well, non-simplicial faces, you are going to end up with an object which will be already large and with many representatives. And so the computation will be difficult. You get it? Okay. So, the bottom line is, even when I'm saying simplicial case is easier than non-simplicial case, yes, it is true in general, and in particular, of course, if you have simplicial cells, the and fall back to the classical differential for simplicial cases. Okay, so I didn't say that, but you could guess that it works as you could imagine. But nevertheless, depending on the number of representatives modulo gamma of your cells, so meaning in the quotient, the complexity of the computation will be very different. So in fact, that's why I was insisting, but unfortunately badly, in the previous lecture, that the core complexity is the number of representatives of the modulo the action of gamma. So, I mean, let's say, suppose that we were in a world where, with the action E8 had only 1 or 2 representatives, then the computation for rank 8 will be already done. Okay. So the main problem is that for E8, you have 240 minimal vectors. Well, and almost all of them are representatives of the big face. So it means that you catch the full geometric complexity of the set. And this, of course, is very bad. There is another thing that I wanted to say, and sorry, I forgot to put the correct slide. So I explained one way to compute the faces, but you could also use tools that you have for polyhedra in order to compute the face. Okay, so if you have if P is let's say d-dimensional polyhedron, you have tools like things that L or the I think CCD library. For computing the d-1 dimensional face. And it is possible to use also this tool for computing the faces, and not the way that I for instance. But when, I mean, those tools have progressed in the past year, and when I tested them, it was slower than the approach that I gave to you. But maybe today, in some case, it could be more interesting, and this approach was used by other colleagues for instance, in the hermitian case computations. So I had to mention this. Okay, so as I was almost giving the intuition in the previous talk, so in fact, the Steinberg module is hidden in the Voronoi complex. So in somehow, I mean, you could describe the Steinberg module using the Voronoi approach, for instance, if you want to have fun. And what has been proved by Soulé is that, in fact, the gamma equivariant homology of the Voronoi complex is isomorphic to the homology of gamma with coefficient in Steinberg. So in other words, the equivariant spectral sequence that I described a few slides ago is the equivariant sequence. I mean, the abutment of the equivariant spectral sequence is given by the homology of gamma with coefficient in the Steinberg module. Okay, that's okay. So of course, so here again, so in order to simplify the setting, so all the results are done for the classical Z case. If you want to do it with OK for K number field, well, maybe not an abstract, not too general number field, but at least an imaginary quadratic field or then, of course, I mean, you will need to adapt the generic torsion. So here, Okay.
Generic torsion is the torsion in the...
Again, the generic torsion is a torsion which is coming from the finite subgroup of the favorite arithmetic group. But yeah. Sorry. I hope that you will be able to cut this. Yes, it is very disruptive. Sorry. Yeah, what I want. Of course, I mean you can ask a question. Why, if you are interested in computing the cohomology of gamma with mod p coefficient, for instance, and write exactly in the generic torsion. Okay, it's fine. But it turns out that there are also a completely different method for doing that. In fact, even some part of the method maybe that I explained Graham last week. So it definitely, I'm not sure that it is the smart way to spectral, the p torsion part of this equivalent spectral sequence, if you are interested by the cohomology of gamma with a coefficient in Fp, for instance. I think that there are better techniques for doing that. Okay, so now from the previous computation, we can, for instance, so this is just an example, just for illustrating. We have plenty of results now on this group using similar computations. And so it just rephrasing the Voronoi complex computation in terms of the homology of gamma with coefficient in Steinberg. So here, just the color code is the one is black, it is more or less easy. Well, let's say more or less straightforward, sorry. Blue is a little bit less straightforward. And for the red one, it means that you have to compute differentials. Differentials in the spectral sequence, so it is a little bit harder. But nevertheless, it is doable. It is just tedious. And strictly speaking, I mean, we should be able to program it. It won't be easier, but we have all the correct formula, and using a tool as GAP and maybe using some part of app, it could be possible to compute it directly. Okay.
Put a square bracket SO with that.
Oh, sorry. Yeah, that's Soule. Okay. Yeah, I didn't. Sorry, I didn't put also the unless I'm mistaken. So Peter, if you, I didn't put the ones which were already computed by Lee Sharba. Of course, Lee Sharba computed part which at the time was not at all easy, and they did everything by hand. So that's quite very courageous. So how does it work? So in fact, well, in order to compute this part, so it's a completely different strategy. And I was hoping to show you an example because it uses gap. In order to do that, we use gap. So mainly, so we have to deal with the stabilizer. So the first thing that we have to do is to explicit the action of the stabilizer. It's not so easy. And what is the smart things to do is to find the maximal subgroup of the stabilizer for which the action is which acts trivially on the cell. And then what you will find. So in this case, the quotient will necessarily be two torsion. So it will be easy to deal with it. And then after, you build a decomposition series on this quotient using gap and using the method that explained Bettina Hecke last week, the same functions. You can try also to identify in a better way the groups. So you have to int a little bit the groups that you get in the stabilizer. I can tell you many, so it is either permutation groups or monoidal groups, so it means group generated by permutation and diagonal coefficients. And could have some large stabilizer. So meaning, you have, in the case already for n equals 7, some stabilizer has at least one has something like 300,000 elements. Okay. And then you apply Linden or Schisser at each level of the decomposition theory. And don't be afraid. Say, yes, you have to manipulate plenty of spectral sequences. But most of the time, so of course, if you are lucky, you will get just 0. You have to track the 0 layer in the different levels of Linden or Schisser spectral sequence. So it is tedious, but reasonable. So of course, it is reasonable to do it as long as you get 0. If you get, unfortunately, a non-trivial element, then you have to trace it to at the bottom, sorry, at the top level of the decomposition theory, and then again to trace it in the spectral sequence, build the differential, and so on.
Is the function in gap resolution normal series?
Yes.
It does that?
Yes? No. Oh, you should trace the element. Yeah. Yeah.
It's called resolution subnormal series. You have a subnormal or resolution normal series, and you give it an n, and it sticks everything.
Yeah. Yeah, but fortunately, as I said, we always add 0, and only to one level where we had to write down the differential. Oh, but again, we have all the tools in order to write down the differential. It's just that it is tedious. If you are used to do that, but it is doable. And you can even compute D5 if you want. Of course, not in the Linden or Schisser spectral sequence, okay, but in the equivalent spectral sequence. So in Linden or Schisser spectral sequence, already, it's a little bit more difficult, or at least I don't know the technique. Okay, so this is the strategy, and so isolate the action in order to summarize, and then use gap in order to compute in some sense, recursively, if you prefer, the homology that you expect to be 0 in this case. Okay, because it is the case. Okay, maybe case when we say that the following group lie in S2 or in S5, so it means that mod this, everything is 0 here. Good. Yeah.
Big torch is even better.
Yeah. So once, as I explained yesterday with the Borel-Serre duality, and it was just a recap of what already explained Jennifer and Peter in their talks. So you end up with the value for the cohomology of the arithmetic group. So of course, you can be intrigued about one point, here we have both GL6 and SL6, and what exactly are we doing? So in fact, first we compute the model for GL6, and then we deduce it for SL6. But when I say we deduce it, the deduction is not trivial. You need to redo some partial computation, because of course now you are not dealing with equivalence mod GL6, but mod SL6. So it means that the complex will be larger. And of course, if you increase the index of the group, so here instead of SL6 you use a congruent subgroup, then again the complex will be way larger. And the computation of the equivalence will be more difficult. Here it is still easy to deal with the SL6. But for congruent subgroups, it is more tricky, and explain why it is difficult to go to high level, for instance. And in the odd case, GL and SL behave the same because the determinant is split. And you don't care about torsion in the Z case, in the Z case. So of course, I mean, here the scenario will be also a little bit different in the Hermitian case, depending of your ring of integer. Okay, so what you deduce, and Peter already speak at the beginning of his talk this morning, is you can apply this to the K-theory. And then you can deduce this. Okay, so potentially we have this class here, and we can deduce that K6Z equals 0. But here, nevertheless, there is a mod 2 on both sides, which is unpleasant. And as we are always lazy, so we just use Voronoi results on the Milnor conjecture in order to get rid of the two torsion part. But dealing with the three torsion is already not easy, and we have to use, let's say, the strategies that I explained yesterday. Okay, so now, what happen if we want to go to higher rank? So you got what I explained. It is not possible to deal with the rank 8 just the same way that we deal with the lower rank. So here is a hint of this complexity here. The perfection rank for rank 8 perfect forms goes from 36, so it is simplicial, to the highest one, which is E8, 120. So I said 240 minimal vectors, but up to sign, of course, only 120. And here you have this, in some sense, the simplicial part, well, the simplicial big cells. And please don't do the lapsus that I just said. So it is not the simplicial part of the complex, because of course you have simplicial cells in the middle, which are coming even from E8 or from E7, for instance, E6, and which are not at all related from the simplicial perfect forms.
And you also have non-simplicial cells in lower dimensions, right? That come from
Yes.
the non-simplicial perfect
Yeah.
forms.
I thought it's what I just said.
No, I think you said the opposite. You said there's simplicial boundaries from the non-simplicial parts, but you also have smaller than 37 in dimension whatever.
Yeah. Okay, yeah. I agree, but yeah, that's
You can't
yeah.
just take the skeleton of
Yeah.
the 37 skeleton. Now it's a simplicial complex.
No,
That would be
no,
great.
exactly, no. No, that won't be so easy. So here, so of course, I mean, you can say that, I mean, the geometry, at least up to 38, is doable. And if you look out, it represents 90% of the form. So of course, you cannot prove that, for instance, that all the information is there. Okay. So maybe you really need one small piece of information which is coming from E8. I don't know. That's also is another problem. And again, unfortunately, not an easy one. But you can at least try to see what you get from the computations. I mean, you just do some experiment. It's what I've tried. And it turns out that already there, I encountered some unpleasant computational problem due exactly to this, because there are, so the dimension is already high enough, and the combinatorics of the simplicial cells for which we have the maximal number of representatives, it is already costly. So, of course, smart ways to deal with that. So maybe I will explain it in the problem tomorrow, in further direction. But on the other hand, you can say, okay, I want only piece of information of the Voronoi complex in rank 8, 9, 10, 11, 12. But only the bottom part, not the top one. Okay? If you look on the slides, on the previous slides, for the data for n equals 6, n equals 7, you will see that we have cells in the bottom part. So the complex is very small at this level. And so the question is, how can we do that? So usually you build the complex from the top to the bottom. And now the idea is how it is possible to build the complex from the bottom to the top. Okay, that's and here again, so you need the mathematics. And it turns out that there are several strategies. I mean, you have a strategy which is maybe a little bit more, let's say, computational, using linear programming, but it is nevertheless to understand the geometry which is hidden in the Voronoi complex. It is of course, I mean, just do linear programming just like that. Okay. Or you can deal directly what we call the Watson index. So in fact, what you look is at quotient, I mean the quotient of subgroup lattice. And this is the approach of Martinet. What you just need to have the number of expected cells. Then after you can generate using random number generation. You can generate the cells as long as you have enough perfect forms that you are aware of. And if you are lucky, of course. Sorry. And so here is the information that we are just missing for instance, if we are interested by computing 8, it's the number of classes modulo GL8 of lowest dimension. So it means 8-dimensional cells. Okay, so you have just 13 class, and you can pick your favorite perfect forms, pick some random minimal vectors, and try to build non-equivalent classes. And it works pretty well. And you don't need so for instance, I was able to build representative for this only with the simplicial cells. Okay, so here are all the results that we get. And in particular, so we have this knowledge on the Voronoi complex. And we can deduce, again, by Boresser duality, the results for the I codimension of the cohomology of GLN. And Peter explained this morning, there are other methods in order to get the top codimension here. Dimension with dimension of the group, of course. Okay, so now, yeah, there is something that I wanted also to emphasize, and this is really curious. Discuss during the week about stabilization map for GLN and other groups. So of course, I mean, the stabilization map from SLN Z to SLN plus 1Z has also a part at the level of the Steinberg module. So you get a stabilization map for the homology of SLN Steinberg N to SLN plus 1 Steinberg N plus 1. And you expect this map to stabilize at some range, meaning that you get an isomorphism. I think that the conjecture is when n is greater than I plus 1. Do you agree? I plus 2, sorry. Yeah. So, yeah, greater. No, yeah. Okay, so it's correct. You can wonder how does it translate at the level of the Voronoi complex, and it turns out that it translates to such map, which is very intriguing, and it is even it is very intriguing because it turns out that we have such a map for n equal 5 from SL6, which is described in our paper. So this map was very intriguing. So I do not claim that this map corresponds to the morphism. And from the purely Voronoi geometry point of view, I mean, this map is not completely natural. And there are no reason why it should be an isomorphism at this level. If you discuss with people who understand the geometry of the Voronoi space from the lattice point of view, I mean, this is completely mysterious. Here, this is natural. I mean, you can expect this. And likely, I mean, you can prove it for, let's say, large band enough. And here, you have something which is a mystery.
Both is a mystery, I think.
But,
yeah.
Okay, I can argue about the first one. But this one is, I mean, we were already surprised by this map in the case n equals 5, which, by the way, give also a splitting at the level of the Voronoi complex.
So the idea of this isomorphism would be that the perfect or the Voronoi domains that come in late, their skeleton don't really matter for the computational in low degrees. Only the ones that come in early. So only the whatever the perfect forms of the Voronoi cells in dimension n correspond to this homology. I don't phrase this well.
Yeah, but I understand what you mean. Yeah, it's in fact, you expect even the contrary.
I mean, and also all of these things should be zero. So it's not just an isomorphism; that should be zero in those places. Isomorphism implies that they're zero.
Wow.
Because if you take
okay, because you're right. Well, yeah, but it depends of I and n. Because those groups are not always zero. Okay, that's.
In the stable range, they are zero. That's if they become stable, then they have to be zero.
Yeah.
Because two consecutive maps together give you a zero map.
Mm-hmm. Yeah. So intriguing, but the map should exist anyway. Okay, so now even harder in some sense. Okay, so what are we going to do when the classification of perfect forms is even not available? Okay, when you have absolutely, where you have just, let's say, weird bounds, but nevertheless, is it possible to say something about it? And it turns out that the answer is yes, because you still have the geometry of the polyhedron, and you can use some, let's say, some bounds coming from the geometry of numbers. They will be very bad, a little bit like the Minkowski bound, for instance, that we use. Not the best bound that we could have, but it is nevertheless very useful. So we can try to do the same and try to go really as far as you can go and bound every piece of the complex, meaning the large cell and the cells in the middle. And then bound the torsion, and at the end bound the torsion on the homology and get bound even the K-theory. So this was an approach which was started by Soulet several years ago, and it turns out that it works pretty well. So in order to be as close as possible than lunchtime, so I will just slightly rush. You will look at the details in the slides, because anyway, I mean the bounds are a little bit technical, and so of course they are coming from bad bounds, and your only knowledge will be the polyhedral geometry of the complex in some sense. So you will be unable to use even some maybe refinement of the Voronoi complex. So it means that you will have, let's say, binomial bounds everywhere, which will be, of course, very large. Okay. So in general of this type, so you can build the first bound by using very rough bound on the number of cells. So you will be and using, of course, so gamma is the Hermite constant, which, by the way, we don't know how to compute in general. And then you will be able to have a bound for the top cells, and from it the K cell for each, let's say K-dimensional cells. Oops. So it is even worse. Okay. So sorry. So here, so here you have in fact doubly exponential. I mean this bound. So it gives you a bound on the torsion of the K-Fourier for all m, not necessarily the part that we already know. And sorry, yeah, that's last slide, but there is okay. So I missed this one. Here you have the quantity, which is so as you can see. So this is exponential. I mean, this bound is really very, very large. Okay. So if you want to have fun, you can already try to compute it even for n equals 3, or even n equals 2. But n equals 3 is already something fun. And then you can try to compute it for n equals 7, for instance. And then you can compare this bound with the concrete computations that I gave to you. And you will see that it's very, very large. Okay, so you get a bound on the torsion of the homology of SLN. Yes, the homology. And a bound on the torsion of the K-Fourier. So from it, in the first lecture, if let's say the asymptotic version of the Kummer-Van Diver conjecture, and I put the definition in the remaining slides. So okay, I will end here, but you will be able to see the definition. And so here we have this piece of the class group of the real part for the cyclotomic fields associated to zeta p. And all those groups vanish as long as that p is, as I said, huge enough, so meaning that p is greater than the bound that we seen just previously. Sorry. And we can perform the same computation for number. And so we have this part which is coming from K4z equals 0. And we have this part coming from Kxz equals 0. This illustrates how it is possible to use somehow the Voronoi geometry in order to deduce arithmetic information, either at the level of, let's say, a class group cyclotomic fields, or at the level of the K-Fourier, but you can also claim that it is the same here. And I will stop here, and tomorrow I will speak of further direction and problems as will do Peter.